Okay, so hello everyone and welcome back to another video. Today I'm going to be explaining the first lesson from nuclear chemistry. In order for us to understand this lesson, we first have to go through some key terms. The first term is nucleons, which is what we call the protons and neutrons together. The second term is a nuclide, which is what we refer to an atom in nuclear chemistry. Now we know that scientists usually identify atoms using two ways. The first way is by writing the mass number as the superscript and the atomic number as a subscript of the atomic symbol. And the second way is by writing the mass number following the atom's name like this. Another definition in this lesson is the mass defect, which is defined as the difference between the mass of an atom and the sum of the masses of its particles. Now, what does this mean? Let's take helium-4 as an example. Helium-4 has two protons, two neutrons, and two electrons, and the combined sum of all of its particles is going to equal to 4.032979. And we can see that the total combined mass is greater than the measured mass of helium-4. And so the measured mass is 0.030377 less than the total combined mass. And this difference is what we call the mass defect. Now, why do we have a mass defect? What happens to the mass? This is explained by Einstein's equation E equals mc squared, where E is the energy, m is the mass defect, and c squared is the speed of light squared. Now, we can see from this equation that mass can be converted to energy and energy can be converted to mass. And so we can see that the mass defect is caused by the conversion of mass to energy when the atomic nucleus is formed. Now we can substitute the mass defect that we found in the previous slide in this equation in order to calculate the energy released. However, before we do that, we must convert the units of the mass defect to kilograms to match the mass units of energy. After we convert it to kilograms, we can substitute it in the equation and multiply it by the speed of light squared to get this value in joules. And this value of joules represents the energy that is released, or what we call the nuclear binding energy. Nuclear binding energy is defined as the energy released when a nucleus is formed from nucleons, and the binding energy per nucleon is found when we divide the binding energy by the number of nucleons in a nuclide. And this value is what we use to compare the stability of different nuclides. Now we know that the higher the binding energy per nucleon, the more stable the nuclide is. From this graph, we can just see that nuclides with intermediate mass numbers usually have higher binding energy per nuclides, like the iron atoms here. However, if the mass number is very low or very high, the binding energy per nucleon is usually lower. Okay, so the band of stability is what we get when we plot the number of protons against the number of neutrons of stable nuclei. And from the band of stability, we can see that atoms with low number of protons or low atomic numbers must have a neutron-proton ratio of approximately 1:1 in order to be stable. An example of this is helium that has two protons and two neutrons. In helium-4, the neutron-proton ratio is going to equal to 1:1. However, as the number of protons increases, the stable neutron-proton ratio has to equal to 1.5:1 in order for the nuclide to be considered stable. An example of this is lead that has an atomic number of 82 and a neutron number of 124. Now, the band of stability is explained by looking at the electrostatic forces and the nuclear forces between protons. Protons repel each other through electrostatic forces. However, the short range of nuclear energy allows the protons to attract only the protons that are close to them. So from this, we can say that as the number of protons increases, the electrostatic repulsion is going to increase so much faster than the nuclear energy. And therefore, in order for us to stabilize the atom, we're going to need more neutrons in order to increase the nuclear energy or the nuclear force that holds the atom together. This is explained by this graph. We can see how the protons repel each other through electric repulsion. However, we can see how the strong nuclear force holds the nucleus together. Okay, now we have to explain that the atoms or the nuclides that lie outside of the band of stability are considered radioactive. This means that they are unstable and they're going to have to undergo transmutation in order to achieve stability. Transmutation is explained as the change in the identity of the nucleus as a result of the change in the number of its protons. Now we know that atoms are identified by their atomic number, which is the number of their protons, and changing that is going to change the identity of the proton, and this is what transmutation is about. And so nuclear energy is a reaction that affects the nucleus of an atom. So unstable atoms are going to undergo a nuclear reaction, which is transmutation. One more thing to know is that in a nuclear reaction, the mass numbers and the atomic numbers must be equal on both sides of the equation. Let's take this first reaction as an example. In this reaction, we can see that on the left side of the equation, this atom has an atomic number of 90. And on the right side of the equation, we have radium and helium with atomic numbers 88 and 2. And we can see that the sum of the atomic numbers is going to equal to 90. The same thing is true for the mass numbers. It's going to have to be equal on both sides of the equation. So if it is 232 on the left side of the equation, the sum of the mass number on the right side of the equation is also going to equal to 232. So if you get a question like this in which you're going to have to identify a missing atom, what you have to do is that you're going to compare the atomic numbers on the right and left side of the equations. And so the missing element or the missing atom is or must have an atomic number of 92 in order for the atomic numbers to be equal on both sides of the equation. The atom that has an atomic number of 92 is uranium. You can find that by looking at the periodic table. And to calculate the mass number of the missing element, you're going to have to subtract 4 from the mass number of plutonium, and we're going to get 238. This is all for today's lesson. I hope this was useful. Thank you for watching.